All right, let's just jump right into this because it's a wild one. We think of light as the fastest thing in the universe, right? It's pure energy, it's untouchable. But what if I told you that scientists have figured out a way to, well, stop it in its tracks, to cool it down, and make it behave not like a wave or even a particle, but like a solid chunk of matter?
Yeah, I know. It sounds completely impossible. Can you really take a beam of light and give it the properties of a solid? That whole idea just feels like it should break all the rules of physics. But, down in the weird world of quantum mechanics, the rules, they get a little flexible. And just when you think you've wrapped your head around that, it gets even stranger. See, we're not just talking about a solid. We're talking about a supersolid. So picture a perfect ice crystal. It's rigid, it has this fixed structure. Now imagine that same crystal could flow through a tiny pipe with absolutely zero friction, like the smoothest liquid you can possibly imagine. That's a supersolid. It's perfectly ordered and perfectly fluid at the exact same time. And yes, scientists have now made one, using nothing but laser light.
Okay, so how on earth is any of this possible? Well, to get how light can become a supersolid, we first have to talk about this truly mind-bending state of matter that makes it all happen. It's all about taking a bunch of particles and making them, well, forget that they're individuals.
That state is called a Bose-Einstein condensate, or a BEC for short. It's an idea that Bose and Einstein came up with almost 100 years ago. Basically, if you take a certain type of particle, like photons, and you get them incredibly cold, like fractions of a degree above absolute zero, and you pack them together, something incredible happens. They stop acting like a bunch of little separate things, and they literally merge into a single unified quantum wave. They become one giant superparticle. But here's the problem. Photons are kind of the ultimate introverts of the particle world. They just don't interact. They'll pass right through each other without a second thought. So how do you get them to cool down and condense together? The trick is a process called thermalization. You have to force them to interact with something else, a medium, that lets them exchange energy and cool off. Think of it like hot steam hitting a cold window. It condenses into water. Same basic idea, but we're doing it with light.
So how do they actually pull this off in the lab? Well, first you trap the photons between two tiny, super reflective mirrors. It's basically a photon box. Then you fill that box with a medium. For a long time, it was organic dye molecules. As the photons bounce back and forth inside the box, they keep hitting these dye molecules, they lose their energy, and eventually, when they're cold enough, they all just collapse into the single lowest energy state possible. And boom, you've got a photon Bose-Einstein condensate.
Now, you might be sitting there thinking, hold on, ordered light that acts as one, isn't that just a laser? And that is an excellent question. Because while they might seem similar, they are fundamentally different things, created in completely different ways. A laser is what we call a non-equilibrium system. It's an artificial high-energy state. You have to pump a ton of energy into it to force all the atoms to get excited and spit out photons that are perfectly in sync. But a photon condensate, that is the state of equilibrium. It's the lowest possible energy state. The photons aren't being forced to do anything. They've just naturally cooled down and settled into the state of perfect order all on their own. And if we dig a little deeper, you can see the key differences. Lasers need something called population inversion, which is just a fancy way of saying you have to get more atoms into an excited state than a relaxed one. But a photon BEC, it doesn't need that. It's created by thermalization. All you need is a high enough density of photons that are allowed to cool down. This is huge because it means you can actually create this super-ordered state of light with less energy than you'd need to make a laser. For a long time, making these photon BECs was this really delicate, fascinating thing you could only do in a lab. The early experiments were amazing, but they had some big limitations. But a very recent breakthrough has pretty much changed the whole game, taking this from a cool concept to something that's actually practical. And the progress has been incredibly fast. So, back in 2010, the first photon BEC was made using that dye-filled cavity we talked about. It was a huge deal. But those organic dyes had a fatal flaw. If you hit them with a continuous beam of light, their electrons would get stuck in these dark states, and the whole process would just shut down. But in 2024, a team made a brilliant switch. They used an inorganic semiconductor instead. Semiconductors don't have those dark states, which meant the condensate could be sustained continuously. This move to semiconductors is, honestly, a massive leap. It means we can have stable condensates that just keep going.
We're using the same kind of tough, well-understood materials that are in our computers and phones. And here's the really big deal. These materials allow for much stronger interactions between the photons, and the whole system can work at room temperature. It's just better, more efficient, and it can even be powered with less energy than a laser.
So we've got this new, really powerful way to make these photon condensates. What does that actually let us do? Well, it brings us right back to where we started, to the absolute weirdest and most exotic states of matter you can think of.
And here we are. Just very recently, researchers took this new semiconductor tech and did what used to be impossible. They took a laser, aimed at a specially patterned piece of gallium arsenide, and used it to control the interactions between the photons. And that forced the photons to condense not just into a fluid-like state, but into a state that also had a rigid crystal structure. They made a real-deal photon supersolid.
And listen, this isn't just a one-off fluke. The experts are saying this is the start of a whole new field. I mean, the researchers who made the semiconductor BEC wrote in Nature Photonics that this technology is what promises access to superfluidity of light and opens the door to using this stuff in real-world quantum tech that works under normal conditions.
The potential here is just enormous. Studying a supersolid made of light is way easier than studying one made of supercold atoms, so it gives us this incredible new window into quantum physics. This could lead to a whole new class of hyper-efficient light sources. And maybe the most exciting thing? These controllable quantum states of light could be the fundamental building blocks for the next generation of quantum computers and sensors.
So we started with this crazy question. Can light be a solid? And it turns out the answer is yes. And it can be something way weirder and more powerful too. By learning how to control the quantum state of light itself, we've basically opened up a whole new frontier in physics. We've managed to teach light how to act like matter. So the real question now is, what are we going to teach it to do next?